Now that we're familiar with derivatives a bit, we can start to think of how they can come up in real-world situations. And that would be any kind of situation that involves change. So optimization problems are one of them, which will be coming up, but another one is growth rate. You may have heard of the term exponential growth, and what the heck is that anyway? Well, exponential growth is the classic snowball effect. As it gets larger, the rate of growth too increases. Examining this mathematically, we could say that the rate of change, or derivative, of the function is proportional to the value of the function itself. Something from biology would be like population, described by capital N, changing over time. The bigger the population, the faster it grows. So we could say dn by dt equals r times n, where r is just some fertility constant. The best place to start is with the exponential growth statement, where f prime of x equals f of x, where the fertility constant we saw in the biology example is 1. From the name, let's try an exponential equation, and for the name of the exponent, let's denote the base of the exponent with the letter e. So now we have f of x equals e to the x as the function that we believe will satisfy the exponential growth equation that we detailed previously. And just so you don't think you missed something, no, we don't know the value of this e number yet. Well, the best place to start is with the definition of the derivative and plugging in our function. After we plug it in, we have f prime of x equals the limit as h approaches 0 of e to the x plus h minus e to the x all divided by h. We can use an exponent rule to turn e to the x plus h into e to the x times e to the h, and then factor out the e to the x term from both terms on top. This leaves us with our expression that f prime of x equals e to the x times the limit as h approaches 0 of e to the h minus 1 divided by h. Noticing that if we replace e to the x with f of x, we get the expression we are looking for, namely f prime of x equals limit as h approaches 0 of e to the h minus 1 over h all times f of x. All there's left to do is find the value of e such that the limit in that equation evaluates to 1. To solve this, we just have to do some simple algebra while applying the limit to both sides. Multiply by h, add 1, and then take the hth root of the entire expression, where the hth root is just to the power of 1 over h, to reveal what the value of e is. Now hold on, you're saying. This is still just a limit. But take out your calculator and plug in smaller and smaller numbers for h, and you will see that this is indeed limiting to a number, and that number is roughly 2.71828, and goes on forever without repeating, just like pi. For many, this is your second number that is considered one of the great numbers in mathematics. It is actually called e, speculated after the man who popularized it, being Leonhard Euler, and in fact, the number is called Euler's number. So after all that work, we now have a function that's derivative is itself, expressed as d by dx e to the x equals e to the x. And this leads to some very important facts in math, but we will leave those for other videos. So what about finding the derivative of non-base e exponents, such as 2 to the x? Well, we just have to do some rearranging, and then we can use our e derivative to do the work for us. The first thing we will need, however, is e's companion logarithm. Just as log base 10 of 10 to the x is x, ln of e to the x, the natural logarithm as it is called, is x, where ln of x undoes the raising e to the power x. With this sorted out, we can express 2 to the x as e to the ln2 to the x. Since e to the ln2 equals 2, using another exponent rule, this expression becomes e to the x ln2, a perfectly differentiable expression. For this, we use the chain rule, where the inner function is x times the natural logarithm of 2. So the derivative becomes the derivative of the inside, being the natural logarithm of 2, times the derivative of the outside function, which doesn't actually change since this is what e to the x does. So the derivative of 2 to the x is natural logarithm of 2 times e to the x ln2. And simplifying the expression on the right gives us that d by dx, 2 to the x, equals the natural log of 2 times 2 to the x, where we can easily see that this follows the same exponential growth rate expression we'd want, but this time the fertility constant, we called it, is the natural logarithm of 2. This process works for any exponential base, so in general, we can say that the derivative of a to the x is ln a times a to the x. Adding exponential equations to the arsenal of derivatives almost lets us compute the derivative of any function, but a calculus needs to be able to find the derivatives of every function, and we still haven't covered inverse functions. So next time, we'll be looking at the derivatives of logarithms and inverse trig functions. And until next time, keep on learning.